Now I'm going to take you through some example problems to show you how to calculate spindle speeds, which is how fast the milling machine is spinning, feed speed, which is how fast it's moving side to side, and then plunge speed, which is how fast you go up and down, and typically how fast you would go down and plunge into materials. So let's start. First thing is cutting speed. So you should define this as the rate of a tool measured in surface feet per minute. Spindle speed is a number of revolutions per minute, or RPMs, that is made by the cutting tool of a machine. And then feed speed is the distance advanced by the cutting tool along the length of the work for every revolution of the spindle. Man, that is really wordy. I would just say feed speed, or feed, is the distance that the cutting tool moves. That's kind of the feed. So a spindle speed formula is defined in RPM, and you divide the cutting speed by the circumference of the tool. So let's, that was neat, huh? Let's take a look at this formula. That little thing going all the way around represents this wheel as it's spinning all the way to this length would be its total circumference, and circumference is found by pi times the diameter. So we divide the cutting speed times 12, we take cutting speed times 12 divided by the circumference, or pi d, and that gives you the spindle speed. So how do we find the cutting speed, CS? You find that in a tool, you find that in a chart. So there's going to be charts that are always given for you on the semester final and on the final at the end of the year. You're going to have a chart that shows you the cutting speeds. So if we're looking at a cutting speed for aluminum, for example, it has a cutting speed of 250. The question is, what spindle speed should be used to mill aluminum with a half-inch end mill? So remember, end mill is the flat part. So we have our formula. You should have this written down. Cutting speed times 12 divided by pi d. So, and it shows it right here. So we substitute 250 in for CS. We have 250 times 12. Do that math first, because if you do this, type it all in your calculator, order of operations will screw you up. Because if you do 250 times 12 divided by pi times 0.5, it won't do the correct order of operations unless you use parentheses. So to be safe, you could just do the top, find out what that equals, do the bottom, find out what that equals, and then divide the two. And the 0.5 inches comes from the half-inch end mill, that's your diameter. So you end up with 1,910 RPMs. Note that there's no decimals here. 0.1 or 0.4 extra RPMs is so insignificant that you don't ever need to record to the decimal. To the nearest single-digit RPM is probably even a little bit too much, but we could go ahead and still record that. So here's another practice one. What spindle speed should be used to mill soft cast iron with a 1/4-inch end mill? So first of all, you need to know soft cast iron is 80 feet per minute. So go ahead and pause this and see if you can calculate the answer for this. Did you get 80 feet times 12? And then the answer of that divided by pi times 2.25, 0.25 from a 1/4 inch, would have given you 1222 RPM. So please, please pause this and just take the extra 30 seconds or 60 seconds to make sure that you know how to do this and you're getting the correct answer. If you're not, call me over and I can help you out with this. The next formula you should write down is how to calculate feed rates. Again, that is how fast you're moving side to side, front to back. Side to side is in the X direction on the milling machine, front to back is in the Y direction on the milling machine. So here's your formula, and FM represents the feed rate in inches per minute. So take a second and just look at the clock right now. If you're going 1 inch per minute, watch the second hand go all the way around, and then just imagine that distance. So 1 inch per minute is a really, really slow feed rate. So just to give you kind of a perspective, FT is feed, and that's in inches per tooth times revolutions, kind of a wild unit there. NT is the number of teeth on the tool, tool, or flutes is another name for that. And then N is the spindle speed. We just got done calculating some spindle speeds. So in order to find the feed rate, you would have to first calculate the spindle speed. So recommended tool feed. So for the feed value, you have a table for that also. And you're always going to want to choose the smaller number on these tables just to be safe and make sure you're not cutting too fast. So we have a face mill, a side mill, and an end mill, and you're really only going to be looking at end mills because that's the tool that we have, is the end mill here. So here's your example. If you're going to calculate the feed rate for end milling aluminum with a 2-flute, half-inch, high-strength steel end mill, HSS is high-strength steel. Probably a good acronym to note. So here's our formula. We need to know that we're doing aluminum, so our end mill feed is 0.005. And that is our FT. So to sort of organize your data here, you're going to want to write down FT equals 0.005. NT equals, well, how many teeth or flutes do you have? Looks like we have 2 based up here. And the next thing is your N value, your spindle speed, we have to calculate. So CS for aluminum cutting speed, if you looked at that original chart, was 250 times 12. And then we take that answer, we divide it by pi times 0.5, and we get that from the half-inch here. That gives you 1,910. So you end up with 0.005 for FT, NT is 2 teeth, and N is 1,910 RPM. Those 3 pieces, that's all you need. You can just fill in the blanks. Multiply all those together, and you're going to get the feed rate. And so if we do that, multiply those together, you get a feed rate of 19.1 inches per minute. And here the tenth actually is relevant because you have such small numbers that you're working with. Now I want you to do this. So if you calculate the aluminum or the feed rate for face milling aluminum with 4 flutes, 3/4 inch high-strength steel end mill, then the first thing you're going to need to do is calculate the spindle speed. So once you plug in the 250 for aluminum and the 0.75, because it's 3/4 inch, you should get 1,273 RPM, and that was rounded to the nearest whole number. Your FT is 0.005, and your number of teeth is 4 teeth, and again we get 0.005, and we end up with multiplying all those together. 0.005 times 4 times 1273 is 25.4 inches per minute. So here's some factors that would affect feed rates. The power of the spindle motor. Ours is moderately powerful. Condition of the cutting tool. If the cutting tool is really dull, then it's not going to cut as well, so you might have to have a higher spindle speed. We have really sharp tools, so we don't have to worry about that. Also the depth of cut. If you're going to go really, really deep into a material, you can't feed as fast because you're cutting a lot more out. And an example of that is if you look closely at this, you may be able to see that there are 2 distinct lines on here, because we cut at one depth all the way around, then we sink down a little lower, cut all the way around, and sink down lower one more time and cut all the way around. And that's just to make sure that you're not cutting too much material and overpowering the machine. Also the quality of the surface finish required. If you want really high quality, then you wouldn't cut at a very fast rate. Too fast and will start to splinter the wood, and that's a real serious issue. Then roughing versus finishing cuts. Do you want it to be a nice smooth or rough? If it's rough, you can go faster. Finish, you go slower with smaller distances in between the mills. And then finally the condition of the machine and strength of the fixture. So the last thing is feed rate at which the mill can plunge into material, and it's very simple. You just take the feed rate that you calculated before, FM, which again stands for feed rate, and you divide it by 2. So we take this previous formula that we had, and we just divide it by 2. Why in the world would we do that? So again, here's plunge feed rate is in inches per minute, and so is feed rate. You do that because as you are plunging straight down, the sharpest cutting edges are on the sides, they're not on the bottom of this bit. So since the sharpest edges are on the side, you can go faster side to side, but you got to go a half speed going down so you don't overwhelm the machine and bog it down. So if you're going to calculate the plunge feed rate for plunging into mild steel, 4-flute, half-inch end mill, then you first have to calculate the spindle speed. So we look up on our table mild steel, which turned out to be 90, and we have a half-inch diameter. We got 687. And what you should sort of note here is mild steel is harder than aluminum, so we have a slower spindle. We have a slower spindle speed, which may sort of make sense in your mind. It may be counterintuitive, but that's really important for you to remember. Then we continue on with our FM formula. We have 4 teeth. Our FT for mild steel end mill gave us a value of 0.002. And so we multiply those together. 0.002 times 4 teeth times 687 and then take the entire answer and divide it by 2 because it's a plunge, and we get 2.7 inches per minute. So we're running this pretty slow, again, because we're cutting mild steel, and the numbers show that that's feed rate is actually going to be pretty slow. So now it's your turn. Calculate the plunge feed rate for plunging copper with a 4-flute 3/4 inch high-strength end mill. So hopefully you calculated the spindle speed to be 509 RPM. Copper had a cutting speed of 100.75 inches for the 3/4 inch diameter. And then the number of teeth was 4 flute, and your end mill for copper is 0.004. So we multiply this together, we divide by 2 again because it's plunge feed rate. So that word plunge is something you really want to be careful to pay attention to, and it ends up with 4 inches per minute. So that looks to me like copper is probably a bit softer than steel, although there are other factors because the size of the bit plays a role, how many flutes plays a role. So that might be a little bit too much of an overgeneralization, but just something that you might take a note. Other operations that require slower speeds, if you're reaming something or counter boring or counter sinking, then you use different values. So 1/4 or 1/2 to 2/3. These are less significant, so you probably don't need to note these down. But if you get really into milling, then that's something that's going to be important if you want to use some of these more advanced bits for completing maybe special projects that you want to work on your own, because you're free to use a milling machine for whatever you want after you've gone through all the safety procedures and you've shown you know how to run it. And then tapping, which would be threading. And we don't actually have any tapping bits, but if you wanted to buy one, you could probably buy one, maybe $10, and then you could have your own tapping bit that you could use in a milling machine. And that's it.